Okay, so unlike the last section, where x was approaching some number, some finite value, here we're going to look at the long-term behavior of graphs. Okay? So right away, I want you to look at the difference between these two expressions. This is a question from section 2.4. And what do we see here? We see x is approaching some fixed number, a. And we're asking the question, or I guess here we're making the statement, that the y values are getting large. Okay? So the sort of the x coordinate on the graph shows up in our direction of approach down here, whereas whatever our y values are approaching shows up in the statement of what the limit is equal to. Okay? Compare that with what we're going to do now. I'm saying what happens to the graph of f as the x values go very far to the right. Okay? And in this case, I'm saying the y values appear to be approaching some particular height as my x values go to the right. Okay? So these are two completely different problems. Okay? All right, let's go ahead and look at the graph of this function. Okay? Does this graph have any vertical asymptotes or holes? Let's be careful here. Jesse, you were shaking your head. Why did you say there's no holes or vertical asymptotes?
Nothing cancels out.
I don't know if I like.
There's no number that would make that 0 on the bottom.
You're both right. Okay. So remember, last time we said vertical asymptotes and holes arise from exclusions in the domain of the function. What number am I not allowed to plug into this function? I can plug in any number I wish, right? Okay. Because what's x squared? It's either positive or 0, and then add 1 to it, it's guaranteed to be positive. How can my denominator ever become 0? And that, of the problematic operations, remember we listed them at one point? Natural logs, tangents, square roots. Of the problematic operations, the only one I'm doing is division. There's no way I could ever divide by 0, so the domain of this function is all real numbers. Okay? And it turns out that the graph of this function, so the numerator factors as x plus 1, x minus 1, that gives me the two zeros of this. If I plug in a 0 for x, I get out a minus 1. And the graph of this function looks something like this. Okay. Notice that as I plug in large numbers for x, like, I don't know, 1,000. Okay. Square 1,000, subtract 1 from it. Then square 1,000, add 1 to it, and look at the ratio between the two. Well, those two numbers are pretty close to each other, right? So their ratio should be pretty darn close to 1. Okay? So what we'd like to do now is describe this behavior. As x gets arbitrarily large going to the right, it appears to me that f of x is, the range values are getting closer and closer to 1. And as x approaches minus infinity, as x heads, so when I read this, I say as x is going to the left.
What's that to the left of the x?
As. Sorry, that's the word as.
Oh, as. Sorry.
Yep, I apologize.
No, you're good.
It's not going to look any better. All right. As x is approaching minus infinity, f of x is also approaching 1 in this case. Okay? So this is how we're going to define a horizontal asymptote if something like this happens. Okay? So let f be defined on the interval a to infinity. Then if as x becomes arbitrarily large, f of x gets arbitrarily close to L. Okay? Or in notation, x approaches infinity, let's say as x approaches infinity, f of x approaches L. Then we're going to write the limit as x approaches infinity of f of x equals L. Okay. The important thing here, folks, is that this is not the same limit that we introduced when we gave the definition of a limit. But it's a similar idea, and the notation is versatile enough to encompass this idea as well. My x values are not approaching some fixed number. So it doesn't match our definition of the limit that we gave, but we're going to use basically the same symbols because it's a similar idea. Okay?
So we're looking kind of for the horizontal asymptote.
This is precisely looking for the horizontal asymptotes, and the way we think about horizontal asymptotes is they're the long-term behavior, meaning as we go far to the right or as we go far to the left, what's the function doing? Good. Okay. Similarly, as x becomes arbitrarily large negative, I missed large negative, I didn't give you enough room for that, sorry. The y values get arbitrarily close to L, we say as x approaches negative infinity, f of x approaches L. Then we say the limit as x approaches minus infinity of f of x is equal to L. Okay? So for the above function f of x, what happened as we went far to the right? As the x values went close to the right, or far to the right, the y values got close to 1. Okay? Same thing as we went the other way, the y values got close to 1. Okay? Yes?
So do these hold kind of the same property that positive infinity and negative infinity have to equal the same value of L for it to be?
Interesting question. To be a horizontal asymptote. The horizontal asymptotes that you encountered most frequently in college algebra, you just had one horizontal asymptote. Maria, you just drew a picture of a graph. What was that graph?
Oh, like the sideways.
Yeah, who is that? Does anyone remember? The arctangent. Think of the arctangents graph. Okay, hopefully you saw the arctangents graph in pre-calc. Its graph had asymptotes at here, and the graph behaved like this. So we did have two different asymptotes. Okay, so they do not have to agree with each other, but we have a horizontal asymptote here. We don't have terms for right horizontal asymptote and left horizontal asymptote. There's just no terms for those.
Okay.
Yes?
So what happens when a function crosses the horizontal asymptote?
No big deal. No big deal at all. We'll look at that here in just a second. Yeah. Keep that question here for just a second further. Okay. So right away, I've now put questions from 2.4 and 2.5 in the same problem. These questions are all from 2.4. These two questions are from 2.5. Okay. So let's quickly answer the 2.4 questions. As we approach and be careful here, folks. Pretty soon I'll fire my graph maker, but I'm just running through the employees like you can't imagine. So, as x is approaching -1, my y values are approaching infinity. Remember, whatever shows up here is a statement about the y values of the graph. Okay? As x is approaching 2, the limit does not exist. But as x approaches 2 from the right, my y values are approaching positive infinity, and as we approach 2 from the left, the y values are approaching negative infinity. Okay. Any questions on that? Yeah, Kevin.
Oh, never mind. I was doing.
That's all right.
Looking at something different.
Okay. Now, this statement here, the infinity here, is a statement about the right long-term behavior. Again, the only reason why I'm writing the symbol infinity there is to save space and time. I should say, as x goes arbitrarily far to the right of the graph, what are the y values doing? Okay. That's what the infinity stands for. There. So as x goes far to the right, where's the graph? doing a bunch of stuff. As we go farther and farther to the right, the y values appear to be getting closer and closer to whom? 4. Okay. As x goes arbitrarily far to the left, the y values appear to be getting closer and closer to 2. Okay? So we just showed that we had vertical asymptotes at x equals -1 and at x equals 2. And we just showed that we have horizontal asymptotes at y equals 4 and at y equals 2. Do you see why I make you give me these equations? Because if I say, what are the asymptotes, and you say 2, I don't know whether you've really got the idea down. Okay? All right. Here it is one more time. It's important to note that horizontal and vertical asymptotes are not related to one another. They are two completely different topics. Vertical asymptotes arise from exclusions in the domain of the function, whereas horizontal asymptotes arise from the long-term behavior. Okay. So here's a statement to Karina's question. A function may cross a horizontal asymptote. Did this function right here ever cross the horizontal asymptote at y equals 4? Yeah, it did right here and it did right here. Right? Well, okay, but further away. Can it cross it further away? Let's think about that. Is there anything that says it can't? It just says it has to keep getting closer and closer to it. Okay? So for example, limits aren't very helpful here, but does the line y equal 2 have a horizontal asymptote? Yeah, at 2. As x goes far to the right, what are the y values doing? Getting closer to 2. Does this ever cross it, touch horizontal asymptote? The whole way, right? Limits aren't very helpful for simple functions, right? Okay. Look at the next page. This function has a horizontal asymptote where? Horizontal asymptote. Long-term behavior. As you go far to the right, not a y-intercept. Horizontal asymptote. As you go far to the right, what are the y values doing? They're getting closer and closer to 2. What about as you go to the left?
Same deal.
Okay, so we could summarize that by saying the limit as x approaches infinity of f of x is equal to 2, and the limit as x approaches infinity of minus infinity of f of x is also equal to 2. Okay. So did this graph ever touch or cross its horizontal asymptote?
Many times.
Many times. The further you go, the closer and closer it gets. That's true. That obeys the definition. But it keeps oscillating around it. This represents, I don't know, maybe like the motion of a spring, right? You peel back a spring and let it go, okay? And it's going to oscillate about its equilibrium position indefinitely, really. It never stops oscillating.
So on like the test, we need to write those both.
So for this question where I asked just to give the asymptotes, this is good enough because it's applied that you're going to be getting it from the graph. Okay?
When I'm saying like what I have to write on the right, I get exactly what you're saying. So it's
Okay.
like the limit of x approaching a bunch of numbers.
As x
to the
gets
right.
large,
Yeah, largely to the right, it approaches 2.
the y values approach 2.
And then you have to say the same thing for the left, but you have to write both of those.
So
Can you say plus or minus infinity?
Sure.
Could you be like plus or minus infinity?
Sure. For this problem, though, let me just add the directions. No work necessary.
Word.
Okay? Where I do require you to show me work is when I just give you the function. But because here I gave you the graph, you don't have to do any work.
Right.
Okay? I'm fine. Yeah. All right. Yeah, great question. Oh, I did want to ask this. Can a graph touch or cross a vertical asymptote?
No.
No, why not?
Because it doesn't exist
Because where do the vertical asymptotes come from?
from numbers that don't exist in the equation.
Exactly, from the exclusions in the domain. So how could you have a point in a place where the function is excluded from existing there? Right? All right.
Are we ever gonna do this asymptotes?
We will. We won't tonight, unfortunately. I was hoping to, but we just got to cut the show a little short. All right, let's look at these graphs here. Here's the graph of 1 over x. Here's the graph of 1 over x cubed. I can't tell the difference between these two graphs without having more points plotted. Okay. Here's the graph of 1 over x squared. We put that up once before. Twice before, I think, actually. There's the graph of 1 over x squared. Here's the graph of 1 over x to the fourth. These are sort of the building blocks of a lot of the rational functions that have asymptotes in them. Okay. So a lot of times what's happening is some sort of shifting of these functions. Okay. So what do we notice? Well, we notice that as x approaches 0, we have vertical asymptotes. And we can describe specifically the behavior. As x approaches 0 from the right, the y values of the odd functions, these odd reciprocal, well, I don't want to say that. These functions that have powers of x in the denominator, okay? If they're an odd power, as x approaches 0 from the right, it approaches infinity. But as it approaches 0 from the left, it approaches negative infinity. But for their even counterparts, it doesn't matter the direction of approach. We're always going to approach infinity. Okay? So that's just summarized right here. Okay? 1 over x to the n has a vertical asymptote at x to the 0. Okay? Specifically, if x is even, then the limit proper is infinity. That's what we saw on the previous page. But if the power is odd, then it depends on the direction of approach. So this is just a summary of what you saw on the previous page. Hopefully it doesn't look like gobbledygook to you. Okay? Because if it does, you need to spend a little bit of time just get more comfortable with this math notation. All right. So we put this up before, but let's just it's nice to put here to contrast. So let's say a positive over a small positive is approaching infinity, and a positive over a small negative is approaching negative infinity. Okay, you can use those facts as you wish. Okay, no work required for them. Okay. Now, if we go back to that set of graphs, these also had horizontal asymptotes, long-term behavior. Okay. And in all of these cases, we had a horizontal asymptote where?
0.
Y equals 0. Okay. So we can summarize that by saying, hey, if we have 1 over x to some power, then there is a horizontal asymptote at y equals 0. Okay. Further, regardless of what constants I have here, I can take an even more complicated expression. So if this were a 2, and this were a 4, and this were a 3, this x term is eventually going to get so big that I have some number divided by something large. 1 divided by 1,000. You've got 1 candy bar, 1,000 friends. How many does each one get? How much does each one get? It goes small, right? It goes small. So this limit is 0. You can use this fact as you need. Okay? So we say that 1 divided by a large positive is approaching 0, and 1 divided by a large negative is approaching 0. Okay? Okay? Here is the trick for doing limits at infinity, meaning the x value is approaching infinity. For these rational functions, you're going to multiply both the numerator and the denominator by 1 over x raised to the highest power seen in the denominator. Okay. That's not how you spell top. Just apply it a little better. This is a tough problem. Okay, I'm going to return to this problem. I do think everyone needs to know how to do this problem. I will test you on it on the exam somehow. Okay. But if you came to the matinee section of this class, I think I lost a lot of people on this first one. So I'd like to move on to an easier problem first. Okay? So we'll come back to that in just a second here. So here I'm asked to evaluate the limit as x approaches infinity. Okay? So the trick for examining the long-term behavior is what I put on the previous page. We're going to multiply this by 1 over x raised to the highest power seen where? In the denominator. Okay? So this is equal to the limit as x approaches infinity of 1 over x to the second divided by 1 over x to the second times the original function. Why to the second power? Because the highest power of x in the denominator comes from this 5x squared term. Okay?
So you do 1 over x divided by 1 over x. Well,
Because I'm going to
in this case, but
because it's going to be multiplied to both the numerator and the denominator.
Gotcha.
Yep.
Gotcha.
So this gives us the limit as x is approaching infinity of, now I'm going to distribute this 1 over x squared term to all terms. So this would give me 3 minus 1 over x minus 2 over x squared, all divided by 5 plus 4 over x plus 1 over x squared. Okay? This first time through, I'm going to show you all the steps. Okay? I normally would not show these steps here in green. Okay? You don't have to show them, but I want to show you how this works out, rather than me just talking through it in the air. I'm now going to distribute the limit to both the numerator and the denominator. Can I do that? As long as the limit of the denominator doesn't come out to be what? 0. So a lot of times when I'm working these problems by myself, I apply the property and then double check it. At the end I say, okay, did the limit of the denominator come out to be 0? No, then it's okay. That's that old phrase, act first, ask for forgiveness later, right? Okay? If you couldn't have used the property, you return and try something else. So let's just go ahead and use the property. I'm going to distribute that limit then to each of the terms in both the numerator and the denominator. This is tedious, I'll give it to you, but let's write it out this first time. Why not? I'm splitting the Ticonderoga profits with you. We've made about 3 cents, folks. So split 76 ways. We're doing okay. Okay. So normally what I would do is I would jump from here to this step here. I wouldn't show this property. Okay, I'm fine with you skipping this step. Okay. But what did we say on the previous page? On the previous page we said, hey, you can use this fact as you wish. A number divided by a large positive approaches 0. Okay. So So let's look at what's happening here. Well, this is the limit of a constant. So that's just the constant. Minus, this is the limit as x approaches infinity. So, right, so 1 over a large positive, that's approaching whom? 0. As is this term. Divided by, this is the limit of a constant, plus 0, plus 0. Okay? This gives me 3/5. Okay, show of hands. How many of you knew that answer before we even started tonight's lecture? Yeah. This is a technique from college algebra. This is a technique from college algebra, right? Not the limit part, but hey, if you're looking for the horizontal asymptotes of a rational function, and the degree of the numerator is the same as the degree of the denominator, you can just look at the ratio of the leading coefficients. You are welcome to use that without showing me any work. But here's the thing. That fact will only get you through this problem. It won't get you through any of the others. So you decide. Okay? I learn how to do the work in the easy problems so I can do the work in the hard problems. Okay? Let's look at this one here. Okay? We're asked to look at the limit as x approaches infinity of the square root of x squared plus 1 minus x. Okay? Just for fun, since we talked about it at the beginning of class, what indeterminate form does this have? What's that, James? Infinity minus infinity. What's happening to the first term, the square root of x term? This is getting large, right? What's happening to this term? It's getting large. And arbitrarily large minus an arbitrarily large is? Yeah, infinity minus infinity, indeterminate form. We cannot say what that's going to come out to be. That's what I'm trying to say. Okay? More work is required for this problem. Okay? So let's go ahead and do this. Okay? We're going to use some version of the trick that we used with our square roots before. And let's go ahead and multiply by the conjugate over itself. Okay. Folks, you don't have to do that. There's other ways to get through this problem. But all ways for getting through this problem involve some way of making this into a fraction as opposed to a sum or difference. Okay? So I like this way. Okay, I'm not going to show the work for foiling out the numerator. Okay. So this gives us x squared plus 1 minus x squared all over the square root of x squared plus 1 plus x. Clean it up just one step more. Save a little room though. We'll have 1 over the square root of x squared plus 1 plus x. Okay? All right. Somebody pointed this out in my earlier class. Unfortunately, there's a shortcut you could take at this point. Okay? So I didn't catch it when I was writing this problem. What's happening? We're getting a fixed number divided by something that's becoming large positive, right? So what is the answer to this going to be? 0. Okay? But I need you to learn a trick that's in that tough one on the back page. I need you to learn a trick for that. Okay? So I'm going to do this. I'm going to keep working on this problem. So you get to see this trick in an easier context because the previous page is a lot harder. If I take 3 times 6 squared x, what can I do with that 6? Yeah, so I mean it would give me a 36 under the radical, and the square root of 36 is 6. And by my square root product property, I could write this as 6 square root of 3x, right? Now, what if I gave you the square root of 3y squared x? can I just say that's going to be y square root of 3x? Why do you say no?
Because it's attached to 3. It's 3y squared.
I mean, we could still, so
No matter what number you plug in.
what if y were taking the place of 6? How does that look different from this one? So you guys are answering no, but you're wrong about your reason. So let's just talk about it. Okay? What if, for this problem here, what if I gave you 3 times negative 6 squared x? What is negative 6 squared? 36. I can pull a factor of 36 out of the radical by writing it as what? 6 square root of 3x.
It's not the same though.
But it's not the same as what was in there to begin with, right? Matters on the sign. How do I pull this y out of the square root? With an absolute value, or with a plus or minus. Okay? So, keeping that in mind, let's suppose I had a 6 sitting out of the radical and I wanted to pass it into the radical. How would I do so? I would pass it in as what?
6 squared.
Exactly, just going backwards with this. Okay? But when I pass something in, so when I pass something inside a radical, it comes in as that factor squared. But the sign also matters. Okay? So let's do it like this. If I have x square root of a, that's equal to x squared a. If we already know that x is greater than or equal to 0, but it's equal to minus square root of x squared a if x is less than 0. See if that makes sense. If I know that x is a negative number, and I pass it inside the square root, well, what was the sign on the original expression, the whole expression, if x were negative? Because square root of a has got to be positive, right? So it's a negative times a positive. The whole expression's negative. If I pass this x inside of here, and I didn't write that negative, this whole expression would now have what sign? Positive. Can't do that. Can't change sign. So I put a negative sign there to keep the fact that x was negative. Okay? This is that tough step that I mentioned on the previous problem. Okay, so hold on to that thought. Okay? I now want to pass, so now I want to simplify this using the technique that we used on the previous problem, saying I'm looking at the long-term behavior of this, so I'm going to multiply by 1 over x raised to the highest exponent seen in the denominator. Okay? The highest exponent seen in the denominator is still basically a first power. Okay? I know there's an x squared there, but I'm essentially just taking the square root, so it's still basically a first power. Okay? So I'm going to multiply this by 1 over x divided by 1 over x. Okay? This gives me the limit as x approaches infinity. Let's try this one. The limit as x approaches infinity of 1 over x in the numerator. And now I'm going to pass this 1 over x inside the square root. Okay? I'm going to do this in a couple of lines. I'm going to pass it in as 1 over x quantity squared times x squared plus 1. Plus 1. Okay? Does everyone see what happened there? No. Okay? So I'm distributing this 1 over x to both terms in the denominator, right? When I distribute the 1 over x to the second term, do you see I get 1 over x times x? That gives me that 1 there. Okay? When I distribute this to the first term, I'm now going to pass 1 over x inside the square root. When something comes inside of a square root, like this 6 here, it comes in as that expression squared. Now, which way is x approaching? It's approaching infinity, which means x will eventually be a what signed number? Positive. So when I pass it inside the square root, I don't have to be so careful.
Oh, so if it was approaching negative infinity, then we would have left that in.
Everyone hear that? If we were approaching negative infinity, then when I passed it inside the square root, I'd have to put a minus sign there to keep in mind that the original expression was negative. Okay. This cleans up to be the limit as x approaches infinity of 1 over x divided by the square root of, now I've got 1 over x squared, and I'm going to distribute to each term here. So this gives me 1 plus 1 over x squared plus 1. Everyone see what happened there? If you don't, stop me. Yes, Dan, thank you. I'm going to distribute 1 over x squared to this first term and to this second term. But what is 1 over x squared? So let's just write out one extra line there. So 1 over x squared is being 1 over x squared is being distributed to x squared plus 1, right? But this is just 1 over x squared being distributed to x squared plus 1. Now I'll distribute it, so I get 1 over x squared times x squared plus 1 over x squared times 1. So there I distribute it. That gives me 1 plus 1 over x squared. All of this was happening inside the square root. So between here and here, that's what I did. How's that work? Good. Okay. Okay. Now I'm going to, so listen to me because I'm not going to write it out. Distribute the limit to both the numerator and the denominator. Then distribute the limit in the denominator to each term. Pass the limit through the square root. Get to all these properties. Essentially we end up with, well, what's this going to be approaching? 0 divided by the square root of 1 plus 0 plus 1, which evaluates to 0. Do we want to talk about that more? The work is similar to what we did up here when I showed you in green, where I distributed the limit everywhere and then started evaluating things. Travis, do you want to go through that?
Why did we even multiply it by 1 over x over 1 over x?
Yeah, great question. So I did say this, that, but I didn't make that very clear. At this point in the problem, you could have recognized the answer was 0, and that would be fine. That won't help you with the tough problem on the previous page, and so that's what I'm building up to. Okay. Okay, so let's go ahead and do that one. All right. I like this problem, first of all, because it starts out, I'm not asking you to evaluate limits. You have to decide what your limit questions are. Okay? So let's first find out if there are any vertical asymptotes to this problem. Well, what do you think?
No. Well, actually, yeah, sorry.
Possibly. I think 5/3 is a candidate to be a vertical asymptote. Let's explore what's happening there. Okay, so let's go look for vertical asymptotes and holes first. So 1, for the vertical asymptotes, we're going to look at the limit as x approaches what? No, not 0.
Infinity?
Not infinity. We're looking for vertical. I heard it. 5/3. We're going to approach 5/3, and we better, since this is to the first power, we better pick a size. From the right, direction of approach. So why am I approaching 5/3? What's the domain of this function? Okay. Well, even though there's a square root, is it problematic? No, because that's the expression inside the square root is always positive. The only problematic operation is division, and I have to be sure not to divide by 0, right? So the domain of this expression goes from minus infinity to 5/3, union with 5/3 to infinity. So, where do vertical asymptotes come from? Exclusions in the domain. So if we're going to be looking for vertical asymptotes, we explore the boundaries of where the domain starts and stops. So we explore what happens at 5/3. Okay. Do I have to show work for a problem like this? Well, is it an indeterminate form? Is my numerator also approaching 0? No, so I can just rationalize my way through this. The numerator is approaching a positive number. When I plug in 5/3 positive and multiply it by 3, I get something just a little bit bigger than 5. Something bigger than 5 minus 5 is small positive. Positive divided by an arbitrarily small positive is approaching infinity. This is enough work to say that we have a vertical asymptote where? So x equals 5/3 is a vertical asymptote. Just for fun, let's go at the other direction. And we get minus infinity. Okay? By the same argument. Questions on that? Okay. So that was a section 2.4 question. Now I want to look and see if there are any horizontal asymptotes to this thing. Let's see if we got any horizontal asymptotes. How are we going to do that?
Check out the long-term action.
Yeah, we're going to look at the long-term behavior of this function, right? So let's pick a direction. Okay? I'm going to look at the limit, and for the interest of time, I'm just going to go ahead and pick minus infinity, and I'm only going to do it for minus infinity because I'm running out of time. Okay? Because this is the hard one of the two. Okay? So this is of the square root of 2x squared plus 1 all over,
3x minus 5.
thank you, 3x minus 5. Okay, what's my trick?
1 over x.
Right? You guys could work on your performance, but you about got it. 1 over x raised to the highest exponent seen in the denominator. Okay? All right. Say these things aloud to yourself. I know you haven't had a chance yet. I'm picking on you. You haven't had a chance to practice it. Okay? But do say these things aloud to yourself. Okay? All right. So here we go. This is equal to the limit as x approaches infinity of 1 over x divided by 1 over x times the square root of 2x squared plus 1 over 3x minus 5. Oops. I lost my direction of approach there. We're approaching whom? Negative infinity. And that makes all the difference in this problem. Okay? Okay. As I let x approach negative infinity, I'm multiplying the numerator and denominator by 1 over x. So let's distribute here. Okay? Does everyone see that that gives me 3 minus 5 over x? Everyone okay with that? Give me thumbs up, thumbs down, thumbs sideways. You don't have to feel good about the whole thing, just I'm talking this step right here. But let me know if you're not feeling so good. I'm looking. Okay? So, I'm going to multiply this 1 over x to the entire denominator. Okay? So I distribute 1 over x to each term. So when I take and multiply 1 over x to 3x minus 5, this gives me 1 over x times 3x minus 1 over x times 5. That's the distributive step, right? Everyone okay with that? Okay. But what is 1 over x times 3x? That just simplifies the x's cancel, and we just get 3, and then I could write this as minus 5 over x. Okay, so that's that step down there. Okay. In the numerator, hold off before you write it down. In the numerator, I'm going to pass this 1 over x inside the square root. It's going to come in as 1 over x quantity squared, right? Okay. Now, I'm going to rewrite that, just to save a little time, as 1 over x squared. Is there a difference between the two?
No.
No. Okay. Times this 2x squared plus 1. But here's the rub. Right? This is what this whole conversation was about. I feel like I could have just showed you this step. You would have been fine if we were only doing the positive direction. When I pass an x where I haven't specified the sign inside the square root, if x is positive, it just goes in as x squared. But if x gets passed in as x squared here, to save the fact that the original expression was negative, I've got to put a minus sign there that wasn't there before. So there's a minus sign there. Okay? All right. How many problems will be like this on your exam? At most, 1. Okay? Probably 1, since I've spent so much time going through it. But please, if I lost you today, please don't say, not going to make it. Okay? But I do want to go through this because I feel like it's something we can all, if you take enough time, I think we can get through it. It's your question. It's your decision, though. Hey, if I take 2-3 hours of study and I'll get this problem down, is that worth the time? I don't know. I'll let you decide the kind of the optimization of that. Maybe it's better to work on some other things instead. Okay? Okay. I now, inside the square root, distribute the 1 over x squared to each term there. Now, as before, I do the whole limit to the numerator, limit to the denominator, pass it through the square root, distribute to all the terms, but eventually I end up with minus the square root of 2 plus 0 all over 3 minus 0. Okay? Everyone see this step to this step? Okay with that? No. Okay? So, we're taking the limit as x is approaching minus infinity of minus square root of 2 plus 1 over x squared over 3 minus 5 over x. I'm now going to distribute the limit to both the numerator and the denominator. Okay? I'm now going to just pass this limit through the square root. And distribute the limit here. Okay. Up above, I've also got to finish distributing that limit out. Now we're ready to evaluate it. Why? Because on the previous page we said you can take it on faith that a positive number divided by a large positive approaches what? 0. Think of that as like 1 divided by 1,000,000. 1 divided by 1,000,000,000. It's eventually going to approach 0. Okay? And the limit of a constant is always still just a constant. So this comes out to be minus the square root. The limit of this constant is 2. This limit, that's x is approaching a large negative number. 1 divided by something large, whether it's positive or negative, is getting small, right? Like 1 over 1,000,000,000. Okay? So that's approaching 0. Divided by, this is just a constant. This is, so 1 divided by a very, very large negative number, like 5 divided by negative 1,000, is approaching 0. Okay? So we end up with, then, minus the square root of 2 over 3. Okay? I'll let you guys on your own time check the other way, the limit as x approaches infinity of the function, and you will find that it comes out to be the square root of 2 over 3. Okay? The only difference in the problem being that I don't have to introduce a negative sign on that square root. That's tough. Okay, that's tough. But I think you can get through that. Okay? All right, we're getting antsy. I got to show you one more problem. All right. So this problem requires a U-Substitution. This is a technique that you're going to use. Well, you've done some U-Substitution problems in your math career. You're going to use them through the rest of your math career. Okay? So we might as well go talk about it now. The idea of a U-Substitution is you look up at an expression, you say, oh my gosh, that expression looks horrible. I don't like that 1 over x expression in there. I would like to replace that 1 over x expression with something simpler. Okay? So what we'll do is replace it with a u. That's nice. Okay? So let's actually formally write out what we're doing. We're saying let u equal 1 over x, right? Now, in math, you can't just wish things away. If you do something, you need to compensate. Okay? So what was happening originally in this limit? X was approaching 0 from the left. But now the variable that's approaching something is u. Well, if x is approaching 0 from the left, what would u be approaching? No? Because look at how they're related. So u would be approaching, somebody said 1 over x, so it would be 1 over a very, very small but negative number, right? So as x goes to 0 from the left, u is going to negative infinity. Do you see that? So here's the relationship that connects u and x together, right? What's x doing? It's getting small. It's approaching 0 from the left. So we're plugging in numbers for x like negative 0.001 or negative 0.02. So what's this expression approaching? Negative infinity. 1 divided by a small negative is approaching negative infinity. Okay? So u would be approaching negative infinity. This problem is easier to work than this problem. To answer this question, you can just fall back on what you know about the graph of e to the x. What is the, or I guess in this case it'd actually be the graph of e to the u. What does the graph of e to the u look like? Looks like this. Okay. So what happens as u approaches negative infinity to the y values of this exponential function? As u is going to negative infinity, what are the y values doing? They're getting closer to 0. So this limit is 0, hence the original limit was 0. All right, folks. That's all of the content from this section. There's some more stuff we could look at, but I'd rather just go ahead and jump into the review next. Okay? So let's go ahead and take a break.